Okay, lecture 58, circular motion. So a couple of things just to start. Who can remember what the formula for the circumference of a circle is? Let's call it C equals?
Pi R2.
Pi R2. What does pi R2 mean? You mean 2 pi R?
Yes.
Oh, okay. Yes, 2 pi R. Right? So that means if I have a radius of, say, 1 unit, then I will travel a little more than 6 units around in a full circle. Okay? So based on this, there's another relationship that we can get. If I draw a little arc with angle theta, it's kind of just a little piece of a circle, you see?
All right.
And we call this, usually we label it with S instead of D. I don't know why. We call it S. I can't even think of a word that sounds like maybe German or French. But anyways, it's just a little piece of the circle, right? And so you can think, well, you know, if I go a full circle around, S would be 2 pi R, right? Where this is R. Of course, this is also R. But if we use theta in radians, right, then 2 pi, that's a full turn all the way around, right? That would be the full distance around. But we can write this relationship S equals R times theta. Right? So you can see that if theta was 2 pi, then this would just be our circumference formula. Okay?
Okay.
So what we're going to be using this result today. Just want to make sure you're familiar with it. I might put it up over here. S equals R theta. And just remember, this has got to be radians. All right, so now we're going to consider this picture here. But before I begin, let's just imagine that we have some mass and we give it a velocity, right?
Yeah.
But now I want to imagine that I've bound this with some string of length r. Okay? So even though initially its velocity is in this direction, it's not going to be able to maintain that direction for very long, right?
Yeah.
This is basically like a rock on a string and you're whirling it over your head, right? So what you're going to get, if you could go all the way around, is a circular path, right?
Yeah.
And everywhere, the velocity vector will be perpendicular to a line drawn from the center of this circle, from this circus. From the center of this circus, that's why they call a circus, by the way, because
Circular.
it comes from Latin circum, which means around. But anyways, so everywhere the velocity will be perpendicular to this. And when it is, it's also going to turn out to be parallel to the little arc length that you get right in this region, okay? And we call that tangential. So what does tangential mean? It means if I have some arbitrary curve, I pick a point on it. If I want to draw a tangent through that, it's a line that passes only through that point, right? This line wouldn't work. No, well, it's not a very straight line. That line wouldn't work. We call that a secant line. But a tangent line is a line that passes just through this one point. You see? So when something is tangential to a curve, that's what it means. It touches the curve, but only at one point. So I think we mentioned this before when we did our optics, or geometric optics, right?
Yeah.
We were interested in tangents, right? We wanted to find a perpendicular, right?
Yeah.
And we wanted to find tangents on a curved circular surface, and so we used the same idea that if we drew a line from the center of the radius of curvature to the surface of the reflective, either the reflective surface or of the glass, right, that we could make a perpendicular, or find a perpendicular by making it perpendicular to that radial line. So anyway, so that's what the velocity is doing on this curved path, okay? We're going to assume, at least for most of this lecture, that the velocity itself, the linear velocity, and that will become clearer in a minute, is a constant value, so it's not changing its linear velocity. But obviously, it's accelerating, right?
Yeah.
Because it's changing direction constantly, right? So we're going to find that there is an acceleration component that is directed inward towards the center of this circle, or circular path. We're going to consider a little angle theta, okay? Now I want you to notice that the vector v1 is perpendicular to the, I should really put vector symbols on all of these. Vector r, well, we'll think of this as a radial vector as well for now, okay? And notice that that v1 is perpendicular to r1, right?
Yeah.
And v2 is perpendicular to r2. Okay, and because r1 and r2 subtend this angle theta, right, that means that if I were to move these velocity vectors such that, here's my v1 and then put, tail to tail, or excuse me, tail to tail with velocity vector v2, right? Then the angle between them will be the same as this angle here. Okay? They're similar triangles. This is one of the harder similar triangles to see. But if you just think about it, right? So R1 and R2 make this angle theta. And here we have a vector, or a line if you want to, V1 and V2, which are perpendicular to each of those, you see? So they're going to make the same angle between them that R1 and R2 makes, you see?
Yes.
So it's a similar triangle, and so we can write that V1 and V2, right, have this angle delta theta right here. And I'm going to draw this. Remember, when we place vectors tail to tail like this is the operation of subtracting two vectors, right?
Yes.
So this we'll call delta V, and it's equal to V1 minus V2. And I'm going to write the scalar V is equal to the magnitude of V1 and the magnitude of V2. Okay? So remember, V1 and V2 are vectors. They have a direction and a magnitude. So it could be, 1 meter per second, north. And at some time later, it's going 1 meter per second east. So the magnitude of that is just disregarding the angle. Okay?
Okay.
So both of these would be equal to, say, 1 meter per second, or whatever this velocity happens to be. Okay?
Okay.
And remember, I said that this is a mass on a string, for example, that is spinning around, and it has a constant linear velocity, and that's what I meant. This magnitude is constant. It doesn't have anything that's accelerating it or slowing it down as it goes. So we're assuming no air resistance or anything like that. Also, let us imagine that delta theta, delta s, the magnitude of this change, delta v, and delta t, which I haven't even talked about yet, but I'll talk about time in just a second. But let's imagine all of these are very small.
All right.
So this would be a gross exaggeration of what I mean by small. When I say the delta theta is small, I mean it's a teeny tiny little change in the angle we're considering, okay?
Okay.
And I can say that delta s is equal to r delta theta. Notice all I've done is I've taken this equation we started with here, s equals r theta,
Yeah.
and I put a little change in it, right? I'm saying we're going to make a little change in it. So delta s is going to change. That means that the distance it's traveled along this circular path is going to be, it's going to change a little bit. And that's going to be because this angle has changed a little bit as it rotated around, okay?
Okay.
The radius, however, is constant, so it's not changing at all, all right?
All right.
So it's like on a fixed string. Well, this, of course, implies that we can write delta theta equals delta s over r, okay? Just solve for delta theta. Similarly, from this triangle over here, the similar triangle, we can write that delta v is equal to v times delta theta, where v is this v, it's the magnitude of v1 or v2, okay?
All right.
Just in complete analogy to it, right? So here the r is this here, the delta theta is this angle here, and the delta s is this distance that we traverse between these two, going from r1 to r2, right? That's the delta s that results from that. Over here, when we go from v1 to v2, we're going to get a delta v, which is going to be equal to the magnitude of v, which doesn't change, times delta theta, right? So it's exactly the same thing, just we're doing it for this triangle instead of this triangle, okay?
All right.
Which means that I can solve for delta theta again. Delta theta equals delta v over v. See that?
Yeah.
Now, can anyone guess what I'm going to do next? I've got these two things that are equal to each other, right? Two things that are equal to delta theta must be equal to each other, right?
Yeah.
There's a transitive property here. So we can write that delta s over r is equal to this change in the velocity up here over v. So now I want to introduce time into it, right? So what does this time have to do with it? Well, imagine that we're motoring along, right? Traveling at this constant velocity, right? What is the distance that I've traveled around this circle? We called it s, right? So I can say that, well, the delta s that I've traveled is going to be equal to the velocity, v, the magnitude of it, right? We're not taking into account the change in direction because we're just assuming we're traveling on this curved path. How far have we traveled? Well, what's our velocity as we travel this path? It's v. Well, all we need to know is how long we've traveled for, and we can get that distance, right? So velocity times distance, or velocity times time, will give us the distance we've traveled. So I can rewrite delta s here as v delta t, where this is the same v as before. So now I have v delta t over r equals this delta v over v. Make sense?
Yes.
If I move things around, I move the delta t underneath the delta v here, and I move this v up here, this will lead us to v squared over r equals delta v over delta t. Well, what do we call a change in velocity divided by a change in time?
Is it acceleration?
It is acceleration, yes. This is an acceleration. And this is a specific kind of acceleration. I'm going to erase this now. We don't need this anymore. I'm going to put the result up here. We call this the centripetal acceleration. So I'll call it A sub c, and it is equal to v squared over r. Okay?
Okay.
So this is the main result from the lesson today, is that the centripetal, that's the acceleration, right, inward, right, is equal to v squared over r. Let me just quickly summarize some of these properties and make an analogy to linear motion. Okay, so I'll write linear over here, and over here I'll write angular. Delta s, if there's a change in the distance along this circular path, that is a linear measurement, right? It's some number of meters, for example, right? So I've moved along a circular path, 5 meters. That's a delta s, okay? The angular equivalent of that is a delta theta. You see? Because when I move this distance delta s, to do so, I've gone through a rotation we'll call delta theta. Make sense?
Yes.
And these two are related by s equals r theta. Okay? So if I want to know how much linear displacement I have, I can answer that if I know how much angular displacement I have. Okay?
Okay.
The tangential or linear velocity is delta s over delta t. What distance did I travel, and how much time did it take to travel that distance, right?
Yes.
That's just velocity, right? But here it's tangential velocity because it's tangential to this circular path, okay?
Okay.
The analogy to this, we're going to call it omega, okay? That's the Greek letter omega. And it is equal to delta theta over delta t. Terrible t, but there. Okay, so take this delta s divided by delta t, that's my velocity, or my tangential velocity. The equivalent to that is take this delta theta divided by delta t, that is my angular velocity. Okay? These are related similarly through v equals r omega. If I just divide both sides of this, right, by delta t, delta s over delta t, that's v. Delta theta over delta t, well that is omega, right?
Yeah.
A sub t, the tangential acceleration. Well, this is just equal to delta v over delta t. The centripetal acceleration, this is kind of the angular equivalent of that. V squared over r, as you recall from here, that was the work from the first part of the lesson, right?
Yeah.
But the centripetal acceleration is v squared over r. And we're going to modify this, though, to put it in terms of these angular units, okay? But first, since delta v is equal to r delta omega, right? We can write that the tangential acceleration is equal to r delta omega over delta t. Because all I did was I divided delta v by delta t.
Yeah.
That is my tangential acceleration from here, right?
Yes.
And that will be equal to r times delta omega divided by delta t. And we're going to call this delta omega over delta t alpha, where alpha is our angular acceleration. So really what I want to write here is that alpha is equal to delta omega over delta t. Okay?
Okay.
That's what alpha is. Now I want to go back to this expression for the centripetal acceleration. V in v squared over r is r omega. So I'll put r omega here, it has to be squared over r. This is going to be r omega squared. So now I've expressed the centripetal acceleration in terms of the angular components. Just a few other terms that might be worth knowing going forward. If we make a full revolution around the circle, we call that a period. Okay?
Okay.
And so the period is defined as from the velocity, right? So if I take 2 pi r, right, that's the distance traveled, and I divide it by the time it takes to travel that full distance, right?
Yeah.
That should be equal to the velocity. So for a full circle, notice that I changed theta here in s equals r theta, right? If I divide at delta s by delta t, that gives me a velocity v, right?
Yeah.
And that will be equal to, if I go all the way around the circle, I've traveled 2 pi radians, right?
Yeah.
Using s equals r theta, multiplying 2 pi radians by r gives me the distance that I've traveled, and this is the time it took to travel that full circle. We call that the period of the revolution, the period of the circular motion.
Okay.
The period of the Earth, right, around the Sun, for example, is 365.25 days. Okay?
Okay.
It's just the time it takes to make a full revolution. Related to this is the frequency, usually written as a cursive or scripty f. That's a terrible one. F is 1 over the period, which in this case would be v over 2 pi r. For example, you might measure the frequency for, say, automobile engines are RPMs. It's revolutions per minute. That's how many times the crankshaft in the middle of the motor spins around per minute. Revolutions per minute, you see?
Yeah.
So that is a frequency measurement. And you can calculate it by taking the time that it takes to do one revolution, right, and then taking the inverse of that, and that should give you the RPMs, or the frequency. Okay?
Okay.
So we'll hear these terms more when we get into oscillations and waves and things like that. We'll use frequency and period. And also with planets, when we talk about Kepler's law, we're going to talk about the period. That's the time it takes to make a full orbit, right? All right. I want to finish with just an example. Okay? I'm going to finish with a pendulum. And I'm going to draw it like this. It's got some mass m hanging on it, so this is suspended and it can rotate about. You've seen a pendulum before, right?
Yes.
And just take a string and tie a rock to it and hold it up and give it a push, right? So let's talk about the forces that are acting on this pendulum, okay? Well, we've got the tension in the line, which will be directed radially, right? And we'll call that T.
All right.
Now, gravity is a little complicated, so we have to break it up into two components. Since this is circular motion, I'll do my best to kind of draw the... Oh, that's terrible. There will be two components. We'll have a centripetal component, and we'll have a tangential component. This is not the easiest thing to draw. Okay, I've drawn a slightly better version of this pendulum that we're considering. Okay? Now, again, we have a tension, which is always directed radially, right? This is towards this rotation point here. You can see the circular path that it's going to follow, right? You can also imagine it swinging all the way around if you want it, right? Let's look at how gravity acts on it, though, okay? So we'll have two components to the gravity. I've drawn the centripetal component, right? This is what is counterbalancing the centripetal acceleration caused by the tension in this line, all right? And this is going to be equal to minus mg cosine of theta, right? The purple is the tangential acceleration, right? I've drawn it in two places, right? Here, so you can see it's tangential to this curved path, right? It's the thing providing the velocity, right? But I've also drawn it over here so you can see how it relates to the angle theta. And this, I guess I could write it in purple, is minus mg sine of theta. Okay?
Okay.
So we've done problems like this before, where we have to break down, like when we did inclined planes, right? We broke the components of gravity up, right? You had one component that was counterbalanced by the normal force on the wood. Do you remember that? So if this is my inclined plane, I've got a block on here, right? There's a normal force which is acting perpendicular to the inclined plane, right? And that has got a component of gravity to it, and the only part that's really affecting it, right, is the component that's in this in this direction, right? Yes?
Yes.
And so that way we can kind of tune the gravity. We can go from no gravity at all with an angle of theta to full gravity if theta equals 90 degrees. So it's the same kind of idea here. But now we can write the components for the centripetal acceleration and for the tangential acceleration of this pendulum. So let's do the centripetal component first. Right? You can see we've got a tension acting in the positive direction and gravity acting in the negative direction, minus mg cosine theta. And this will be equal to, partition that off, this will be equal to the centripetal acceleration, right? So we're going to use mass m times the centripetal acceleration, v squared over r. That's the right thing to put on that side of the equation. Remember, the sum of the forces equals mass times acceleration. Well, the acceleration over here is v squared over r, because it's the centripetal acceleration. Okay, it's the thing that keeps the circular path in place. Okay.
Okay.
Now, in comparison, the tangential component, I should really label this. I don't know if that's spelled right, but let's hope that it is. And then let's write over here the tangential component. That looks like minus mg sine theta, right, is equal to mass times the tangential acceleration. So if I solve this for the tangential acceleration, I'll get that at is equal to minus g sine theta. The masses cancel, right? So that is this component here. So let's talk about a couple of things for this. Imagine that this swung up such that the angle theta was 180 degrees, right? That would be with this block was all the way up here, right? So what does 180 degrees look like? I'll just draw it really small here. That's straight down. 180 degrees would be as if this thing was upside down, basically, right? It rotated 180 degrees, okay? Yes?
Yeah.
Who has a calculator on them? Is it in degree or radian mode?
It's in degree mode.
Okay.
Radian.
If it was in radian mode, we'd use pi, right, for 180 degrees. But type in cosine of 180 degrees and see what it gives you.
It said -1.
Minus 1, that's correct. It's minus 1. The cosine of 0 degrees is 1. The cosine of minus 180 degrees is minus 1. If we look at the graph of the sine or cosine, you can see that that's the case. So if I write t minus mg times cosine of 180 degrees, that's going to be minus 1, so I change it to plus mg equals mv squared over r. So I'm going to ask the question, what is the minimum velocity? You can imagine if you're swinging this thing, you'll need some velocity to make it swing around, right?
Yes.
You can't just have a small velocity, just give it a little push. It's not going to swing all the way around. So think of this as like a roller coaster problem. How fast do we have to be going on the roller coaster so that it can do a loop-to-loop, right, and not just fall down or roll back down the hill, right? Similar to that. So what is the velocity I need? Well, at the top, right, of its path, the tension will be 0, right?
Yeah.
Because the forces, right, we have the tension pulling this way, but gravity is going to take over 100% and provide all of the centripetal acceleration you need, right?
All right.
So the tension of the line will be 0, okay? So at 180 degrees, this will go to 0. And what do we get? We can cancel the m's out, right? And solve for the velocity. We're going to get v equals the square root of g times r. So using that, you can figure out what velocity you need to maintain
Okay.
that circle. Okay?
All right.
So that's just a kind of lame application of this. But we'll talk about orbits and stuff later. And those will be more interesting, I think. I want to do a homework problem for you guys that is similar to this. That's why I showed it to you. It's a bucket, right? So you're going to imagine having a pail of water, right? And you're going to swing it around in a circle like this, okay? And the question is, how fast do you have to swing it so that the water doesn't spill out and fall on your head, okay?
All right.
So understanding how we came up with this velocity should give you some insight into how to solve that problem, which is why I did it. Okay?
All right.
So that's circular motion. That's all I'm going to say about that.